Hello, everybody, and welcome back to A View from Earth, brought to you by Fisk Planetarium at CU Boulder. Hope you guys are all doing well, staying safe. Now, as with the rest of the university and many public spaces around the world, Fisk's Theater is closed to the public for the foreseeable future due to the COVID-19 epidemic. However, we are still so committed and excited to bring astronomy and education to you that we've started a whole host of free online offerings so we can stay connected and keep bringing you this content that you know and love, plus some new stuff like this podcast. So thanks for tuning in and learning with us here today. My name is Tara Tomlinson. I am a planetary scientist and a CU alum. I'm also a presenter here at Fisk Planetarium and the outreach coordinator. And we have Colin here as well. Hi, Colin.
Hey there, I'm Colin Sinclair. I am a presenter at Fisk, and also I'm an undergrad at CU studying astronomy.
So this week we're going to be talking about Mars. Aside from Earth, Mars is the most explored planet in the solar system. Also the only planet in our solar system exclusively inhabited by robots, as far as we know. But today's guests, we're going to be talking with Andrew Wilcoski and Dr. Dave Brain. They're going to be telling us a little bit about Mars's geology, some of the cool ice and atmosphere interactions that happen there, as well as some cool stuff about Mars exploration and some upcoming missions that are on the docket. But first, the news.
All right, and today, to give us a bit of the news regarding Mars, we are joined by Jordan Marsk. Jordan, could you introduce yourself for us really quick?
Hi, my name is Jordan Marski. I'm an former student at CU who recently graduated with a bachelor's degree in astronomy, and I was coming to talk about the new Perseverance rover that's set to launch next month and start collecting data on Mars next year. The Perseverance rover, I think, is really cool because it's going to be looking for like ancient signs of life on Mars and looking for signs of like how habitable Mars used to be. And it's going to be taking a lot of soil samples. It's going to have a drill on it so it can drill like a little deeper into the surface. And it's just going to be looking for like signs of water, signs of like fossils of like microscopic like microbial life and things like that. And another thing that I thought was really cool is Ingenuity. I'm not sure if you guys have heard of that, but it's like a small little helicopter that they're going to be attaching to Perseverance to test just like flight on Mars to see if that's like a possibility. And like they're just going to be doing small little flight tests with this little like drone helicopter that I think is kind of cool. But other than that, it's also going to be testing things like it's going to be testing producing oxygen on the planet to see if we can like do any like things like that for like human habitation. And just like it's going to be analyzing weather patterns that it experiences on the planet, and just all around just like looking for like areas that we could possibly like build a base on or something like that, and just like preparing for future human exploration of the planet. But yeah, and the mission is going to last at least one Mars year, which is around 2 Earth years, specifically like 687 Earth days. But much like the previous Mars rovers, it's very possible that it will be useful for much longer than that, and can get a lot of data. But it's scheduled to land on Mars on February 8th of 2021. So that will be fun to look forward to, assuming that launch goes as planned and everything.
Very cool. So this is Mars 2020, right? Which is just, not recently, but you know, in the past couple of months been renamed Perseverance. That's its new mission name.
And yeah, I like the name a lot.
Yeah, it is kind of cool. And it kind of seems almost timely now with everything going on in 2020. It's like, we're persevering through 2020,
Yeah.
continuing to do science, which is kind of funny because I think it was named kind of before everything got crazy, but here we are.
Yeah, they
So-
had a naming contest for different age groups through school kids, essentially. So there was like an
cool.
elementary school and
Yeah.
a middle school and a high school, and I think this was like a fourth grader, maybe. I could be wrong on that, but they won the name. So there was a whole long list, and then they narrowed it down to the top 10 or whatever, and they were all, we like to name things very appropriately: curiosity, spirit, opportunity. Now we have
Oh, yeah.
perseverance. So
Imagine being the fourth grader that got to name a Mars rover.
right? How
I
cool
would
is
be
that?
so excited.
That is awesome. Very cool. Well, looks like we have just under 40 days until the launch window opens. So we are really kind of getting in close to this. And by the time this episode is, it will be even closer. So
Yeah.
it's very exciting. Cool. Well, great. I think that's a great little intro for our discussion about Mars that will be coming up. So Jordan, thanks so much for putting that together for us and doing the research and preparing your presentation. That was a lot of fun to hear about that.
Oh yeah, thank you.
Hey everybody, so our guest for today is Andrew Wilcoski. He is a grad student at CU Boulder studying geophysical and atmospheric processes on Mars's polar ice caps. His current work looks at kind of how the ice caps change over time due to things like weather and atmosphere, and even like the location and orientation of the planet in space. It's super complicated, but really cool. So thanks for joining us, Andrew.
Yeah, it's good to be here.
Happy to have you. So I figured we start off with kind of a basic question that's actually probably more complicated than it seems. But so you study the polar ice caps on Mars, and they're actually kind of similar to the ice caps that we have here on Earth. Can you give us kind of a brief explanation of why ice caps form in polar regions like this, and what kind of criteria go into the formation of an ice cap?
Yeah, that's actually a really great question. So there's really two main things that control whether or not you're going to get an ice cap on any particular planet. And those two things are the first is really temperature, basically how cold it is in whatever region you're trying to form your ice cap. And the second is basically whether or not there's water available to form that ice cap. So the reason that ice caps tend to form in polar regions is just because it tends to be colder in polar regions. So the reason it's colder in polar regions is basically because those regions get less sunlight overall, or less direct sunlight, than you do, say, at the equator or what have you.
Makes sense. Easy enough. So yeah, we see these ice caps at the poles, and wanted to kind of jump into a little bit of history that some people don't really know, and we think this is pretty cool. So back in 1877, there was this Italian astronomer Schiaparelli who discovered what he thought were canals on Mars just by looking through his telescope, saw these weird lines and things. And another American, Percival Lowell, kind of jumped on that, and they got really excited about this idea of maybe beings on Mars making canals to divert water from the poles down to the equatorial areas where it's warmer, things might live better. So we know now, obviously, that that is not a thing. There are not people on Mars building canals. But our question is, would this even make sense? Is this a thing that could be done? Say, if humans wanted to go and live on Mars in these areas where there's not a lot of water, could they actually build canals and divert water from the poles?
Yeah, I mean, I think that's definitely an interesting idea, and it's something people are talking about in I guess the Mars exploration community. The ice caps on Mars are some of the largest and definitely the most conspicuous sources of water ice. So they're definitely obvious choices for water ice. I believe that if you send humans to Mars, there's basically like two major things that you would need water for, and that's one is, you know, for drinking and consuming and whatnot on a human level. But then the second and probably actually maybe even most important one is making fuel for rockets, so you could get back off the planet. But the question of whether or not it'd be feasible or practical to like transport water from long distances, like over the surface, is definitely an interesting one, and one I'm not personally super familiar with. I think there's, you know, you can imagine there's plenty of logistical things like that. Like, do you build a pipeline all the way from the poles to like the regions you actually want to inhabit because they're, you know, warmer or whatever? Or do you land straight by the poles, you know, where your water ice is available? There's also one of the interesting things though is that there's also a lot of water ice that isn't in the polar regions of Mars. So there's lots of ground ice. We see lots of evidence for ground ice, you know, as low as you know, the mid latitudes, 40 degrees latitude or whatever. So another way you could potentially access ice on Mars is just land at a lower latitude where you want to live because it's colder. You know, you have sunlight to fuel your solar panels or whatever, and then, you know, go drilling for ice.
All right. So now your work specifically focuses on surface and atmosphere interactions, how the two kind of work together. And most people think of that as things like rain and snow and dust storms. Are there any other sort of interactions that we see between the Martian surface and its atmosphere?
Yeah, there's a bunch of fascinating stuff going on between the Martian surface and the atmosphere. So yeah, I think you're right. Like on Earth, we're mostly familiar with, you know, like rainfall or like, yeah, snowfall, things like that, wind, dust, sandstorms, and there's similar things on Mars. Definitely, there's not rain, but there is snowfall, largely in the form of carbon dioxide snowfall. It's unclear whether or not there's water ice snowfall, so the same kind of snow we're used to here on Earth. I don't think that we've observed that directly yet, but there's lots and lots of CO2 snowfall. The main way that my research, or the main like atmosphere surface interaction my research considers, is actually water vapor in the atmosphere condensing directly into ice. So basically skipping the snowfall phase and going straight onto the surface. And then kind of the reverse process, which is sublimation, which is ice turning directly into water vapor in the atmosphere. Basically the surface pressures and temperatures on Mars aren't, it's not warm enough and the pressures aren't high enough to support liquid water. So Mars just skips the liquid water phase and only really dilly-dallies in the vapor and solid ice phases. But there's also other crazy stuff going on just because Mars has a lot of CO2 ice and atmosphere interactions. So the Martian atmosphere is mostly carbon dioxide. It's like 95% carbon dioxide. And what that means is that, well, in addition to that, there are regions on the Martian surface that are basically cold enough to support CO2 ice. And so there's all these interactions that go on between carbon dioxide ice and all of the carbon dioxide that's in the atmosphere. So things like CO2 geysers near the South Pole that, you know, shoot up dust into the atmosphere that then settles back down into makes these weird spidery looking things, and all sorts of, yeah, just kind of wacky stuff like that we don't have on Earth.
So really quick, if I could jump in, you mentioned that Mars it's not really hospitable to liquid anything. So going back to Tara's question about the kind of, feasibility of transporting, liquid water from the polar ice caps to the equatorial region, if you weren't doing that in some sort of technology that could pressurize it and keep it at the right temperature, that would be completely impossible, right? Because that water would just then evaporate or vaporize, and there would be no liquid to transport anyways. Is that right?
Yeah, that's totally correct. So basically, if your water is exposed straight to the atmosphere, like it would be in a canal,
Right.
then yeah, it would just evaporate before it would really go anywhere in liquid form. So you'd have to have some sort of like pressurized pipe system to transport it, basically.
So a couple minutes, maybe it was more than a couple earlier, you mentioned that something like 95% of Mars's atmosphere is CO2, carbon dioxide, right? Here on Earth, humans are now figuring out that we should maybe stop putting CO2 everywhere because it's not good for our atmosphere and for the life that our planet hosts because of the greenhouse effect, right? Where the CO2 will trap the light that makes things hot, and then it will get really hot, and then we end up with a situation in a very, very bad scenario. We end up in a situation like Venus, where the surface is hundreds of degrees Fahrenheit. Why is Mars so cold when its atmosphere is made almost entirely of this greenhouse gas? Well, I would think that it would start to trap all of this heat, and kind of reflect it and put it back down on the surface. So what is missing there?
So that's a really great question. And there's the short answer is that atmospheres are really complicated. I think that the slightly longer answer is, I think that a big reason why Mars's atmosphere doesn't have a really strong greenhouse effect is you have to remember that it's really thin. So it's not a lot of CO2. It's not a whole lot of CO2. The other thing is because CO2 is the major atmospheric constituent, like basically almost but not quite the only thing making up the atmosphere. There's a lot of really complicated interactions with, like, in addition to the greenhouse effect. Like, for instance, you can also get carbon dioxide clouds on Mars. So say you up the amount of carbon dioxide in the Martian atmosphere, but now clouds are more likely to form. Well, clouds tend to actually they can actually have a cooling effect on a planet because clouds are really reflective, so they can prevent sunlight from reaching the surface and things like that. So yeah, I guess the answer to that question is just that atmospheres are super dynamic and very complicated. One of the reasons the CO2 factor is kind of almost more straightforward on Earth, is just because carbon dioxide, even though the levels of carbon dioxide in the atmosphere that are causing climate change here on Earth are significant enough to do that, there's still a really small percentage of the actual atmospheric composition. So you don't get weird things like CO2 clouds forming, and like weird atmospheric surface interactions as far as the CO2 component of the atmosphere is concerned.
So it sounds like it's just always a good idea to keep in mind that you really need to consider the atmosphere in its entirety, not just one constituent of the atmosphere. And
Yeah,
that
exactly.
all of those things will interact with each other to create different situations.
Yeah, and yeah, there's all sorts of domino effects that happen in atmospheres. Just like you change one thing, thinking you create a hypothetical atmosphere and you change one thing thinking it'll like make the planet warmer, and that really has all these other effects that end up making it cooler or something. The interesting thing about climate change here on Earth is we've sort of accidentally performed an experiment, a very high consequence experiment, but we've done it nonetheless, where, okay, we actually did increase the amount of carbon dioxide, and we saw, okay, like, yes, it did increased surface temperatures, and it still is. And we have lots of data and evidence to support that. But it's not always a given. Like we can understand why that happens, but it's not always a given. Like there's lots of stuff you need to take into account.
And that's one of the reasons it's so hard to sort of counteract. We can't just take CO2 out of the air and think it's going to fix everything, or, adjust this lever or flip this switch and think that it's going to go back, because we have no idea how it's going to affect all of this other stuff that's going on.
Yeah, exactly.
So great. Well, that concludes our kind of list of questions that we had prepared. And we do have several, we're calling them, I don't know if Tara mentioned the name, we're calling these Capcom Q&A. Kind of, people send us their questions and we relay them to our experts, being you. Christine from Austin asks the following: if we find life on Mars, how do we know we didn't bring it there with us?
What a great question. So there's this whole field of, I guess, there's this whole field of space policy called planetary protection. And basically what planetary protection is all about, it's when people say planetary protection, they mean it in a biological sense. So basically preventing, Earth life from contaminating potential Mars life, or like potential Mars life from contaminating, Earth life or whatever. And this is something that people have been thinking about since the Apollo era. People were terrified. That's why you see those images of the astronauts like cooped up in that tiny trailer in quarantine for God knows how long after they got back from the moon, because we legitimately didn't know, like, are there microbes on the moon that, like, if introduced to the Earth will just like wipe out all life on Earth. That's like a super, that's a pretty like out there, idea, but you may as well be responsible about that sort of thing. And then the same is true, so like you send astronauts to Mars, what's like, and then you send those astronauts to like get a sample, and then you test that sample and find life there. It's like, okay, how do we know that the astronauts didn't bring that themselves? At least as far as robotic exploration is concerned, NASA has very strict policies about like basically decontaminating their spacecraft. So anything you're going to send to planetary bodies that are in like this certain class of planetary bodies that like could potentially host life, like Mars, has to be like extremely decontaminated. So basically like they are extremely careful when they're putting the spacecraft together, and then they also do things like they blast it with a bunch of radiation while it's still on Earth to like make sure it doesn't have anything living on it or whatever. And then there's other spacecraft where it's like, oh, this spacecraft, like, it's not gonna go to the surface of any planet. It's just gonna stay in space. It's not even gonna go near any planet that could potentially harbor life. So like, it doesn't really matter if we like aren't, super hardcore about decontaminating it. But when you start sending human missions, that's kind of a different story, because like by definition, you're sending life. You're sending humans themselves, and then you're sending like, the entire microbiome that exists inside of human beings. And I think that it's a big question whether or not, like, if you sent a human mission, whether or not you would send a human mission to a spot, like say to a sub-region on Mars that you're like pretty dang sure could harbor life. Like maybe you send humans like slightly outside of that region, and then they use robots to actually explore that region, so that you like, have a greater margin for error as far as, contamination is concerned. But that's a really good question, and kind of a big roadblock to responsibly exploring a lot of these regions, in the search for extraterrestrial life.
Andrew, it was such a blast to talk with you, and I learned a lot today. Like, even being a student in APS at CU, this was a very enlightening hour for me, hour and 15 minutes for me. So thank you for that. That was a lot of fun.
Yeah, sweet. Thanks for having me. This was super fun.
Today, we are joined by Dr. Dave Brain, who is a professor at CU Boulder and a researcher for the Laboratory for Atmospheric and Space Physics, also known as LASP. He specializes in atmospheres and magnetospheres at Mars and elsewhere in the solar system, and is a member of the MAVEN spacecraft team, which is currently studying Mars's atmosphere. He is also a science advisor for the Emirates Mars Mission, or EMM, a new and exciting mission originating in the United Arab Emirates that plans to provide a complete picture of the Martian atmosphere at high altitudes and close to the surface. Dr. David Brain, thanks so much for being here with us today.
Thanks for having me.
So I am of the, you mentioned that one of the reasons that this atmosphere is important, or an atmosphere, is to maintain the correct pressure and temperature for liquid water. As we know, we do not see liquid water on the surface of Mars today. But we do see perhaps some signatures that it was there in the past. What happened, to the best of our understanding as the scientific community, what happened to Mars's atmosphere such that at one point in time it allowed for liquid water, but today it doesn't do that?
Yeah, it's a puzzle that we're still trying to piece together all of the details. But I think at a very high level, we can say what happened to the atmosphere of Mars. So as you said, there's evidence on the surface that liquid water used to be present. This is both chemical evidence in terms of some of the minerals that we see that required liquid water, and even the shapes of surface features that suggest that liquid water once flowed or sat there. That means the atmosphere had to have been thick enough to support the liquid water. The atmosphere is not sufficiently thick today. So the 0th order answer to your question is that the atmosphere was lost. We can give a little more detail than that as well. Some of the atmosphere we know was lost to space. And that's those atoms and molecules in the atmosphere got enough energy to escape the gravity of the planet. And that's part of my research area and my involvement in the MAVEN mission, is thinking about how much atmosphere from Mars could have been lost to space, and it's a lot. But that's not the whole story either. We are very confident that some of the atmosphere was lost down to the surface and the subsurface. We're also confident that part of the atmosphere has been lost to the surface and subsurface of the planet. The planet's red because it basically rusted. That's pulling oxygen out of the atmosphere. We see polar caps on Mars, which if Mars gets cold enough are going to grow and grow and grow. And we have plenty of evidence that atmosphere has gone down to the surface and subsurface as well. So the combination of these two things, loss of atmosphere to space and loss of atmosphere to the surface and subsurface together, we believe has changed the atmosphere enough that liquid water is now very difficult to have be stable on the surface of the planet.
So in the past, we as humans, collectively have kind of relied on the government institutions like NASA to do the job of putting people in space and doing that, space science and research. But like you mentioned today, we're kind of seeing more involvement from kind of like private companies, SpaceX being the obvious example, and I guess that idea of having these private space industry players can be a bit controversial within the astronomy community. Getting to Mars has been a huge push within parts of the private space industry. And that's one of Elon Musk's whole things is let's go to Mars. Do you see any particular pros or cons involved with, kind of invoking the private industry in the huge undertaking of going to another planet?
Yeah, and I'm glad that you cast the question in that way. I think they're both pros and cons. I'll preface it with a statement that private industry has always been involved in human exploration. And the change more recently is being involved at sort of the idea level, the top level. But, the space shuttle, many different parts of the space shuttle were contracted out to private industry. When we sent the MAVEN spacecraft to Mars, certain circuit boards or certain aspects of that are always contracted out. And when the rockets that we put our spacecraft on, many of them are built by ULA down in Denver. So private industry has always been involved in space exploration, and the change we're seeing here is Elon Musk. The change we're seeing here is Elon Musk and SpaceX having a plan for start to finish, making it happen themselves. Jeff Bezos being involved, Blue Origin being involved, these companies that want to do the whole thing themselves. So that's the big change. Some of the pros are that private industry is less risk averse than government. Every time a mistake is made or an accident happens, people correctly go back and examine why that happened, put procedures in place to prevent that from ever happening again. And this is all done not maliciously in any way. It's done out of care for human life, which we should always be very careful about. But it also ends up putting on layers and layers and layers of bureaucracy when it's run by government sometimes, and that can slow things down and make things a little more expensive. Private companies have the privilege or are in a position to be risk averse and to move very quickly. And I hear sometimes about the very early days of NASA in the early 60s and even into the late 60s, when people were there, late into the evening and all through the weekend, and it was really energetic. And those are the same kinds of things that I hear about the people at SpaceX today, moving just as quickly and just as fast and being just as passionate about what they're doing. And people at NASA today are super passionate, but the two modes, private industry and government, just move at kind of different paces sometimes and with different amounts of expense. The same con, that same thing that's a pro is also a con. If you're more risk averse, then more accidents are likely to happen. And when we're talking about sending humans to a place where we can't go rescue them, that's something to think really carefully about before you do it. A second thing for maybe the scientific community is the fact that private industry doesn't always have scientific interests at heart and their root cause. Sometimes there are noble causes involved, but at the end of the day, the company won't exist unless they can make money by doing it, which means that they have a ranked priority list, and tetanus isn't necessarily at the top or the bottom of their list. And so in terms of not preserving Mars, but in terms of learning everything we can about Mars without first interfering with the things that we want to study, is maybe not at the top of the priority list for private industry. And so one thing I've been told in terms of in my positions on sort of national service committees, thinking about what our priorities are for Mars exploration, I've been told that we need to put our science priorities that would be tampered with if once humans land on Mars, we need to put those at the top of our list now, because humans are headed there and there's no stopping it. So that's something I think about as a con from the perspective of a scientist, is contaminating the planet, interfering with the things that we actually want to study.
I think I'll turn over the interview to Tara at this point, and she'll ask you some questions about your research.
Great.
Yeah, we'll switch gears a little bit. So you did talk a little bit about MAVEN already and some of the cool things about Mars's atmosphere that we've learned, but can you give us kind of an overview of MAVEN in general, since I know that's a big deal for you kind of right now? What are some of the really cool things that we've learned? It's been up there a little while.
Yeah, first a brief introduction to MAVEN. It's a mission that was proposed out of the University of Colorado. It was competing against, I think, 22 other mission proposals from all around the country, and was ultimately chosen as the winning proposal to send to Mars. It's a very large undertaking. I think maybe the largest research award in the history of the university or something like that. And I started working on this in 2004 when I was a postdoc. I didn't have children until 2006. So I've been working on MAVEN longer than I've had children. And it's been orbiting Mars since 2014. And the whole goal of the mission is to figure out what happened to the atmosphere and climate over the last 4 billion years of the planet's history. Did enough atmosphere escape to space to explain a big transition from a habitable planet to a non-habitable planet? So maybe the biggest result from MAVEN so far is that we estimate that a lot of atmosphere was lost. And that's how we wrote the paper. It was just a lot. That's what we wrote. No, I'm just kidding. We tried to put constraints on that. And the error bars are large, but maybe half of an Earth atmosphere in terms of pressure, that would be called half a bar. Maybe more than a bar of atmosphere has been lost to space over time. So these really cool physics processes that happen to particles at the top of the atmosphere are not just cool physics, which interests me, but they may have been important for the entire life cycle of the planet so far, which excites me. So that's one reason I like thinking about MAVEN science. There are some unexpected things that have been observed by MAVEN. For example, aurora in the atmosphere happening far away from any planetary magnetic field signatures. So this is maybe the first time we've recognized that you don't need a magnetic field to get aurora on planets. All sorts of new processes for making particles energized and moving them away from a planet. And I could go on and on and on, but I'll stop there.
Excellent. And so MAVEN's been up there and we've learned a lot from it. And now you're also involved in the Emirates Mars mission, which is a new mission, which is super exciting, that's going again to study Mars's atmosphere. Can you tell us a little bit about EMM in general and kind of how it's different and what it's doing differently than MAVEN?
Yeah, so let me start with in general, and then, as you said, move to the science. The Emirates Mars mission started as a mission concept in 2014, and it's a collaboration with an agency, a space center in the United Arab Emirates. And they approached some institutions to be academic partners in their effort to send a spacecraft to another planet. The UAE has sent spacecraft into orbit around Earth, I think 3 times before at this point, but had never sent a spacecraft to another planet. And so asked for some partners to help figure out how to do that. So it's a very interesting day in your academic life when someone walks into your office and says, we would like to send a spacecraft to Mars. What would you like it to do? And there were ideas all around, but everyone was soliciting ideas, and it was a fun exercise. So now this mission will launch next month in July. The launch window opens July 14th and stays open through early August. And so we could try each day to get the spacecraft off the ground and headed on its way to Mars. And one thing I didn't mention is the programmatic goals of this mission. You can edit all this later because I know this is way too long. One thing I didn't mention were the programmatic goals of this mission. One of the goals was to send a spacecraft to Mars for the 50th anniversary of the country. And so the country will be 50 years old very soon, and they want to do something big for this. And if you know anything about the UAE, you know that they tend to go big. They currently have the tallest building in the world, for example, the Burj Khalifa. They make land out where there was no land before in the shape of a map of the world. They're used to undertaking big projects. And so they wanted to send a spacecraft to Mars for the 50th anniversary of their country. That wasn't enough to get me really on board or excited. But when they told me why they wanted to do it, then I was in. They want to do it to help diversify their economy. They know that the oil economy won't last forever, and they want to transition to a knowledge economy. They want to be an example for young people in that part of the world of what you can do when you pursue big projects like this. They also want to join the international science community and more specifically, the international space science community. And they want to develop space science and engineering as something that parents would want to tell their children to think about pursuing in that part of the world. And then when I met the science team, it was 100% female at the time that I met the science team, which shattered my expectations for that part of the world. And I admit that I was ignorant and had never been there and had not had a lot of interaction there. But now I have some lifelong friends from the UAE, I'm sure. And all of these programmatic goals got me on board pretty quickly. The science of EMM is very interesting. It's an orbiting spacecraft, and it's going to study both the lower atmosphere and the upper atmosphere. And it has 3 science instruments on board that work at 3 different wavelengths. There's a camera that takes visible images. There's an infrared instrument that probes the lower atmosphere, including temperature and composition. And there's an ultraviolet instrument that probes the upper atmosphere. And the idea is to figure out how energy moves through the atmosphere. You could think of energy as temperature of the particles, if you want, because that's the energy that they carry. But how does this energy get transported from place to place? How does it vary with Martian day? How does it vary geographically? How does it vary with season and year on Mars? And in order to do this, the orbit of the spacecraft is very special compared to any previous spacecraft to go to Mars. Most previous spacecraft orbit up and down over the poles, which means out of necessity, which means that out of necessity, they always orbit at a single local time. So maybe 3 p.m. and 3 a.m. And if you want to understand the atmosphere of a planet, you might immediately realize that that's not ideal. It's like asking everyone on Earth to go outside at 3 p.m. today and take some measurements of the atmosphere and then run back inside and then use the measurements from 3 p.m. to figure out weather on the planet. That's not going to work. At the same time, we have rovers on the surface of the planet, like Curiosity, that's making temperature measurements and atmosphere measurements really great. You can't understand the atmosphere of a whole planet that way. That's like asking the people in Boulder to make measurements around the clock and tell people in the rainforests of Brazil how their atmosphere should be working. That's not going to happen either. So this spacecraft orbits in such a way that it observes every geographic region of the planet at every time of day, every 10 days. So Olympus Mons, the big volcano on Mars, will have atmospheric measurements above Olympus Mons at every time of day, every 10 days. And so the orbit helps us tie those measurements together to understand circulation patterns and energy transport and bottom to top of the atmosphere as well. How changes near the bottom of the atmosphere propagate upward to the top and result in atmospheric escape.
This is actually, I have what might be kind of a tough question. I don't know, but I'll ask it anyways, which is, as you and Tara were talking kind of about the cultural importance for the UAE of going to space and what that will look like, it made me remember, that there's a lot of people on Earth that, in the past and today that have asked the question, why, or I should say not ask the question, but hold the sentiment, that we should focus on Earth issues rather than focusing energy on space, right? Especially you take today's climate, right? There's a lot going on with the coronavirus and with systemic racism. And people are saying, well, why, shouldn't we just pause things like space exploration and space travel and fix these problems first? How can you focus on these other issues while we have this at hand? And that's always been a thing, right? In the 60s with going to the moon, it was Vietnam. And today, it's what I said. And I think there will probably continue to be that kind of reaction to science and space travel. Do you have any, how do you respond to when someone tells you that sort of thing? And I know this is kind of a tough question, so we don't have to go there, but I'm curious to see what you think about that.
Let's go there. That's fine. And it is a hard question, and I don't know that I have fully decided what my answer is, but I've been asked this question. I was asked this question by another faculty member at the University of Colorado before the fall 2019 semester. And first of all, I think the question presents a false choice. I don't think it's either or. I think it can be both, and I think it's important to be both. I don't think we should abandon the problems that we're facing on Earth, from systemic racism to climate to coronavirus, to making sure that our planet is a place where we can not only survive, but be happy. We shouldn't abandon those things, and neither do I think we should abandon the big ideas that come from exploring space, that come from pushing ourselves in that direction, that come from wondering if we're alone. I think if nothing else, doing those things provides inspiration. And inspiration is important when you're tackling problems close to home. I've talked already in our conversation too about the all eggs in one basket aspect. And as much as I'd like to think we can and will fix all the problems facing us here, I worry that there will someday be a problem that we can't control and that we don't have a solution for. And so maybe the practical side of me also wants to see us continue to send spacecraft to really cool places. That's got to be part of it too. But I think it's a false choice.
Very well said. I like that you know, we don't have to break it into either or. That's nice. And for fun, an example of an unstoppable problem might be, like you said earlier, in 5 billion years when our star dies.
Yeah.
Unless technology has really just gone off the wire, that would be a tough thing to say. Please don't. We'd like to stay here a little longer.
So, okay, so that was all the questions we had for you today. Thank you so much, David Brain, for joining us. We're very happy to have you on our podcast.
Thank you for having me. It was fun.
We'd like to thank our guests, Andrew Wilcoski and Dr. Dave Brain, for taking the time to chat with us about Mars today. And if during those interviews you felt, man, I'd really like to hear all about this, you can. We have the full extended interviews available on YouTube and SoundCloud. So go ahead and check those out if you feel so intrigued that you want to do so. And remember to come back next week for a discussion about the far reaches of our solar system. We'll be talking with Dr. Fran Bagenal about the New Horizons mission, which went to Pluto. And we'll also talk about a citizen science project looking for basically the shadows of stars with Ryder Strauss about the Recon Network. This podcast is available on YouTube, SoundCloud, Spotify, and Apple Music. And we'd like to invite everyone to visit our website, colorado.edu/FISC, where you can see a schedule of our upcoming show topics and guests. There's also an option for you to submit your questions, and we can pose those questions to future experts that we have on the air, or otherwise get those answered for you. So if you have any burning questions that you'd like to figure out the answers to, send us a message. You can use the website form or just email us at fiscpodcast@colorado.edu. Make sure to comment and subscribe so that you don't miss the next episode.